Hello everyone. Today we are going to talk about the statistical interval. That's another part or another method of doing estimation. So remember, the previous methods of estimation that we have learned, they all fall under the category of point estimators. So basically, our estimate of a particular unknown parameter, like the mean of the population, for example, was a value. So we design an equation. The equation allows us to combine the samples, and then based on that combined value of the samples, we could actually figure out an estimated value, single value. So that's why we call it point estimation, point estimators, point estimate, right? Well, in many cases, this is actually not sufficient, because as we saw before, every time you get a different sample, you get actually a different estimate or point estimate of the parameter, and accordingly, you cannot really be sure how accurate is your estimation. Another method of doing the estimation is, rather than estimating what is the actual value of the parameter, can actually estimate a region, an interval, over which we think the parameter will fall or will belong to, with a certain confidence level, which is a certain probability level. Okay. So again, instead of in the point estimation case, we were simply saying that the estimate of mu, call that mu hat, was actually equal to some value. Let's say, for example, 3.819, whatever the value is. That's a point estimate, right? We would say that mu belongs to a particular interval. We call that the confidence interval. And we define that interval as starting, let's say, from 3.719 until 3.919, for example. And mu is somewhere inside this region with a particular confidence level, which is the probability that mu belongs to the confidence interval, right? So that's nice, right? Because that is more suitable to the nature of random variables. Now the question is how we can actually do this, and we will study here in this course, in the scope of this course, we'll study two cases of estimating the mean of a normal distribution. So we'll always assume that our population is normal distribution, and we are trying to estimate the mean, mu, because estimating other parameters will result in other final results different from what we will get here. In two cases, case number one, the variance of the population is known. Case number two, the variance of the population is unknown, but the number of samples is large. So when the variance is known, we don't care about the number of samples. When the variance is unknown, it makes a big difference whether the number of samples is large or not. And we'll see that later on. Okay. So again, here it just talks about what's a confidence interval versus what was the point estimation concept that we have studied earlier. So it says that earlier we actually looked at the point estimate of a parameter, which is calculated directly from the sample data, and as we said, it just gives you a value, right? So mu hat is equal to, for example, the sample mean, and if I substitute the values of the samples, I'll just get 1,000, for example. Okay, so that's basically point estimation. Okay, now again, as I just mentioned earlier, sampling variability. Every time you pick a sample, there are different values because those samples are random variables, as we have discussed earlier. So basically, every time you will get a slightly different value of mu hat, and in fact, it's very difficult to get a mu hat which is exactly equal to the true mean of the population mu, except if you address the whole population, and we don't want to do that because of reasons that we mentioned earlier again. Okay. So basically, okay, out of all these numbers, which one should I pick? That's a difficult question to answer. But it's easier to say that the mean or the parameter that I want to estimate is in a certain range, for example. Again, similar to what I gave you in the introductory slide. And in that case, we call that an interval estimate. And that interval, we call it the confidence interval, the interval that we think that with high confidence, with high probability, the mean or the true parameter that we are trying to estimate is within, belongs to, right? And that basically, if I want to be more precise, I would like that interval to be smaller, because I don't want the range of the parameter possibilities to be very large, because this means that I don't know exactly what's the parameter. But not only that, I want it to be smaller, and I want the probability that the parameter belongs to it be higher. And these two objectives, so I want the confidence interval to be as small as possible, while the confidence level to be as high as possible. This is what's desired. Okay, but reality is those two objectives are contradicting. If you make the confidence interval smaller, the probability that the parameter falls inside it becomes smaller as well. If you make the confidence interval larger, the probability that the parameter falls inside it becomes larger. So these two objectives that I want to achieve here are contradicting. And the only way to resolve that contradiction is to use the number of samples that I want to pick. So basically, by increasing the number of samples, I can make the confidence level higher for the same interval, or I can make the confidence interval smaller for the same confidence level, just by increasing the number of samples. And of course, if the number of samples reaches the whole population, then in that case, the confidence interval will become zero size, it will become a single point, and the confidence level will go to 1, which is the case that I can actually get the true parameter rather than estimating it, right? Okay. Now let's see, how do we define the confidence interval? There is some kind of like explanation where these relations come from. You can find that explanation in the book. The simple situation is as follows. We know that if we are trying to estimate the mu hat, the mean of a normal population, then as we looked at from the point estimation point of view, the best estimator for that, if we are dealing with a normal population where the variance is known, is going to be x bar, the sample mean. And we know that the sample mean itself is a random variable. And we know what's the mean of the sample mean. It's again the true mean of the population. And what is the variance? So it's normal distribution, that sample mean, x bar. And it has a mean equal to the true mean of the population, and it has a variance equal to the variance of the population divided by the number of samples. And knowing this information, we can actually figure out the probability that the sample mean, right? Since we know its distribution, we can figure out the probability that the sample mean falls in a certain interval, right? And that interval basically what's the probability that the sample mean is in a certain interval, and then accordingly what's the probability that mu is within that interval. So without going through the derivations, which are not difficult, you can read them in the book as I mentioned, the result is that if you select a confidence interval with an upper limit and a lower limit, we call that two-sided confidence interval, right? Such that it is centered at the sample mean. So So the sample mean is the center of that confidence interval. Then the probability that mu belongs to this sample mean, belongs to this interval. So the probability that mu belongs to this confidence interval, right, to the confidence interval, is going to be equal to some value. We call that value 1 minus alpha. We just name it 1 minus alpha. And if that probability is equal to 1 minus alpha, the probability that the true mean belongs to the confidence interval, if we call that 1 minus alpha, then the interval itself, lower and upper values, will be represented by this equation. Okay, so this is the lower, and this one is the upper bound. So we can say that mu is greater than this lower bound, smaller than the upper bound, with a probability equal to 1 minus alpha. Okay. Now, what are the terms here? Very easy. X bar is the actual sample mean. So if you have a set of samples, you just substitute them into the sample mean equation, the sum of the samples divided by their number, and you can get X bar. Sigma is the variance of the population. We said that we are dealing with a normally distributed population with known variance. So sigma is known. Definitely, if we know the samples, then we know the number of samples that we have. That's n. Then after that, we need to figure out the remaining parameter, which is z alpha over 2. So z alpha over 2 is defined as the probability that the standard normal distribution is less than 1 minus alpha over 2, which is basically represented by what we see here. So remember that this is your confidence interval, and the confidence level is the probability of existing in this region. And then this is called 1 minus alpha. If I want to figure out the probability of existing in this region all the way back, is actually equal to 1 minus alpha over 2, as we mentioned. So basically, this is how we get the z alpha over 2, right? The z that corresponds to this probability, as we just mentioned. So quickly, the properties of the confidence interval. It's an interval that contains the true mean with certain probability. We call that probability the confidence level, and this is the lower limit, and this is the upper limit of this interval. And we've already seen how to calculate all the different parameters involved in these two limits. And we'll see once we solve a quick numeric example on this, how it works out. Okay. So basically, here we describe just the flow of how we ended up with this situation. So if you have samples, n samples that are coming from a normal distribution with a mean mu and a known variance sigma square, the sample mean becomes normally distributed, but the mean in that case, as I mentioned here, becomes mu, and the variance becomes sigma square over n. Then if I want to standardize this sample mean, then I will subtract the mean, divide by the standard deviation, and that will give me a standard normal distribution Z. The probability that this standardized is greater than minus Z alpha over 2, smaller than Z alpha over 2, is called 1 minus alpha, or becomes 1 minus alpha, and this is basically this without standardization. So this probability is exactly equal to the probability of belonging to the confidence interval. Okay, again, don't worry about the derivation. A more important thing here is, again, you need to understand a little bit, but the more important thing here is to be able to use the confidence interval correctly in solving estimation problems or interval estimation problems. One important thing is that we call the difference between the true mean and the sample mean, which is at the center of the confidence interval, as we said, we call that the error, right? And the maximum possible error in this case is basically this whole thing. So the maximum possible error is simply this value, right? Z alpha over 2 multiplied by sigma divided by root m. Okay. Again, just an important note from a meaning point of view, the length of the confidence interval is a measure of the precision of estimation. So the longer, the less precision you have. But of course, the higher confidence you have that your mean is gonna fall in that region. If you make it bigger, then there are higher possibilities that the mean belongs to it. But it's less precision in terms of really being more definitive about the value of the true mean, mu, that you are trying to estimate. Okay. So let's look at this example. It says that an ASTM standard E32 defines standard test method for notched bar impact testing. So you have metals, you want to test their strength, and in order to test their strength, you create a particular standardized notch, and then you hit them with a certain impact, and that impact is measured in joules, and then you see whether they break or not, and that will define their strength, right? And then it talks about a specimen of the A238, which is some kind of an alloy, right? And it was measured under that standardized notch impact test to see where it breaks, and at the temperature of 60 degrees Celsius. These are the results of the impact in joule that causes the different samples to break down, right? Now, assuming that the impact energy is normally distributed with a standard deviation equal to 1 joule, we want to find a 95% confidence interval for the mean impact force or the mean impact energy. Okay. Now, in order to be able to find a 95 confidence interval, now we know that our confidence interval, right, is unknown. That's what we want to find. But we know that the confidence level is that 95%, which is basically 0.95. And as we said, this is basically 1 minus alpha. 95, which is equal to 0.95. And this is basically, as we described earlier, is our 1 minus alpha. So we can figure out that alpha is equal to 0.05, right? If this is 1 minus alpha, then we can figure out the value of alpha, and accordingly we can get alpha over 2, which is 0.025, right? So now we know alpha over 2. We go to the standard normal distribution table, and using this value of alpha over 2, we can accordingly find out that 1 minus alpha over 2 is going to be equal to 0.975, and then we take this value 0.975, we plug it into the probability values inside the standard normal distribution table, and accordingly we got the corresponding value for Z alpha over 2. So Z alpha over 2 is equal to 1.96, as we can see from the result that we got from the table. Then we take this 1.96 and we plug it into the definition of the confidence interval, and accordingly we can find the confidence interval, which corresponds to a confidence level 95%. We call that a 95% confidence interval, okay, which has a confidence level 0.95. Okay. Similarly, we can look also in the same example, we can look for a confidence interval of 90%. In that case, alpha over 2 is going to be equal to 0.05. So we are looking for 1 minus alpha over 2, which is 1 minus this value, which is 0.95. Look it up in the table. That's approximately where it exists. Accordingly, we can get the corresponding Z alpha over 2. Z alpha over 2 in this case is going to be Z alpha over 2 in this case is going to be 1.64. 1.64. We take this value, we plug it into the definition of the confidence interval, and accordingly, once we plug this into the definition, we can get the corresponding confidence interval, right? So that basically shows how this proceeds. Now recall that earlier we have discussed actually the concept in a couple of slides ago. We have discussed the maximum error that can occur in estimating the mean of a normally distributed population. Remember, we said that this maximum error between the actual value of mu and the maximum possible shift that it can go up to is going to be like 1/2 of so we are using x bar, right, to estimate the value of mu. Mu might be shifted from the location of x bar. This is where mu is. Can be shifted to the left or shifted to the right. The maximum distance between them can reach this maximum value. We call that E, the maximum possible error. And we found that this maximum possible error is defined by Z alpha over 2 multiplied by sigma divided by the root of n. This is equal to the maximum possible error, right? This whole half of the interval, right? And then accordingly from this, we can get an expression for n, which is given here. That's what we see here. And this allows us actually to use a third parameter to control our precision. If we want to achieve a certain confidence level within a certain width of the confidence interval, and the width of the confidence interval is going to be 2e. So the whole confidence interval, right, which is centered around x bar, has an e from this side and an e from this side. So the whole size here is 2e. So if I know the whole width of the confidence interval, I can get the value of e. And for a particular confidence level, I can figure out the Z alpha over 2 accordingly. This means that if I plug these into this equation, so the Z alpha over 2 and the E, I can actually figure out a value for the number of samples required to achieve this particular precision. Precision here is identified by a certain value for the confidence interval and a certain value of confidence level, the probability of belonging to that interval. And that allows me actually to increase my precision. Now, when will I reach a point estimate accuracy? I will only be able to estimate the value of mu completely accurate only if I address the whole population, right? In that case, I will have a probability or a confidence level equal to 1 and a size of the confidence interval equal to 0, right? So to reach a point estimate, I need to go with n up until either I have infinite number of samples or I reach the size of the population, right? That's one thing. And the other thing to keep in mind as well is I can reach a confidence level equal to 100% if I make my confidence interval span the whole possible values of the random variable. So I make it very wide such that it covers all the possible values of the random variable. Now in this case, again, I don't have that much precision, right? So that's basically more or less the other aspect of this issue, which is there are 3 parameters now: confidence level, confidence interval, and a number of samples. Typically, I want the confidence level to be as high as possible. I want the confidence interval to be as small as possible. And those are 2 contradicting objectives, as I mentioned earlier. And the only way to justify both of them for certain values is to play with the number of samples going up. Okay. Now, this particular example that we see here is actually looking at the precision of our confidence interval. So again, we will notice from the previous solutions that we have done that, for example, we were looking for a confidence level of 95%. Now, the question is, why did we pick 95%? Again, we could have actually aimed for a better. Let's say we aim for a 99%. But what would happen in that case is that you will notice if you solve for the 99%, for the 95%, this is the length of the confidence interval that you will get. If you solve for the 99%, you will notice that the confidence interval length has went up. So basically, as we said before, the higher the confidence level, the bigger the confidence interval. And that's not what we want. So accordingly, as I mentioned, again, just to notice the precision, if you increase confidence level, you get wider confidence interval. If you want to reduce the confidence interval, then your confidence level will go low, given that you are using, in all these cases, a fixed number of samples. If you want to achieve reduction of the size of the confidence interval, so making it smaller with higher probability, with higher 1 minus alpha, right? Then in this case, you need to increase the number of samples to a certain level to achieve that, as we mentioned earlier, and this way you can get both precision factors adjusted as you want. Another important variation of the confidence interval calculations is, so far we have been discussing confidence intervals that are called two-sided. So you have a lower bound, you have a lower bound L, you have an upper bound U, and you have your center, which is X bar, and your actual or true parameter, the mean of the population, is somewhere inside this confidence interval, right, with a certain probability of mu, right, belonging to the confidence interval is what we call the confidence level, is our confidence level, right? But the important thing is that the region itself has an upper and a lower bound, and is symmetric around, it is symmetric around the sample mean X bar. That's what we mentioned earlier in terms of properties and the two-sided. We call that the two-sided confidence interval. Now, in some cases, your confidence interval is only upper bounded or is only lower bounded. So this is an upper confidence interval. This is a lower confidence interval. Mu is greater than a certain value, or mu is less than a certain value. So basically, you have a certain upper bound, and your mu belongs to this with a certain probability, right? And goes all the way to minus infinity. That's an upper bounded confidence interval, right? Or you have a lower bound, and your mu belongs to somewhere into that whole duration that goes from the right side all the way to infinity. The only difference in this case is that if we look at the curves, we are trying to get the probability that mu is less than this value, right? Or the probability that mu is greater than this value. In both of these cases, if this is 1 minus alpha, then this part must be alpha only, right? And accordingly, we use a Z alpha instead of Z alpha over 2, because we don't have a lower bound, and then we are just calculating the probability of being less than half of that hashed region. We are actually calculating the probability of being less than the whole hashed region. So accordingly, we use Z alpha. Z alpha is equal to the Z that corresponds to a probability equal to 1 minus alpha, right? So basically, it's the probability that your standard normal distribution is it's the Z that corresponds to the probability, the Z that corresponds to, not equal to, the Z that corresponds to the probability of being less than 1 minus alpha. So the upper bounded part, as I mentioned here, this becomes your alpha, right? And in this case, we simply use 1 minus alpha instead of 1 minus alpha over 2 to look up the table. That's in the one-sided confidence. We call these one-sided confidence intervals, and the example here shows you that. So assume that we use the same data that we have seen before, right? A one-sided 95% confidence interval for the mean impact energy. Recall that we find that X bar is equal to this, right? And sigma is equal to this. We have calculated those earlier when we solved this example earlier for the two-sided, and the number of samples is 10. Then accordingly, I want the lower bound. The lower bound is equal to X bar minus, instead of Z alpha over 2, it becomes Z alpha because it's single-sided, one-sided, multiplied by sigma over root n. And that Z alpha is simply 1 minus alpha, which is my confidence level, which is 0.95. And we looked up the corresponding Z for 0.95. It becomes 1.64 multiplied by sigma divided by root n. And that becomes, again, what we see here is actually my confidence interval. It's one-sided, right? An important thing is that so far, when we assume that sigma is known, we ended up with the random variable mu that we were looking at was distributed, normally distributed, with a mean equal to the true mean of the population, mu. And so we ended up with x bar, the random variable that we use for estimating the mu. We ended up with this x bar with a normal distribution with a mean equal to the mean of the population and a variance equal to the variance of the population divided by n, right? This is the case where sigma was known to us, because in that case, what we get is just a linear combination of set of random variables. So when we want to get the standardized case, we subtract the mean, we divide by the variance, so it becomes x bar minus mu divided by sigma over root n. All of these are constant values, known constant values, so z becomes a standard normal distribution, because we know that x bar is already a normal distribution since we sample from a normal population, right? Now the issue is, if sigma is unknown, then our only way to figure it out is to get it from the root of s square, and that s square is equal to the summation of x minus mu, right? These are the samples, you square those and then you divide by m minus 1. Now notice here that this is not a linear combination of the random variables xi, and accordingly we cannot really say that this is a normal distribution, and it's not a constant as well, right? So accordingly, if sigma is unknown and we use s to estimate sigma, to substitute the value of sigma, use the sample standard deviation or the sample variance, the root of the sample variance, then in this case we cannot really say that this z is a normal distribution, because it's not only x bar that's normal, but also that's a random, but also this is a random, and then the relation here is not linear, so I cannot really figure out the distribution of z. In fact, the distribution of z in this case has been studied extensively in the literature and was found to follow something called the T-student distribution, right? However, this is out of the scope of what we will look at in this course. We don't want to go into the complications of dealing with the T-student distribution, even though it belongs to the book. You will find this in the chapter in the book, but we have opted for not teaching this part. Now there is a special case if the number of samples n is very large. So this means that this s, right, is going to be a combination of too many random variables combined together, and theoretically, even though this is out of the scope of this book, you can also show that the central limit theorem can be used here, and it will allow us to assume that this is approximately going to be a normal distribution, and accordingly also again from another kick in of the central limit theorem, we can eventually figure out that this can be approximated by a normal distribution. So in the case that the variance of the population is unknown, if the number of samples is small, cannot really solve the problem. It can be solved using the T-student distribution, which we did not study. It's very similar to the normal distribution, but has different tables and values for the probabilities. However, if the number of samples n is large, then we solve as before. So we construct our confidence interval with the same definition, mu is greater than and less than, and it's x bar minus sigma, but we don't need sigma, so we use s multiplied by x bar minus s multiplied by sigma over, x bar minus z alpha over 2 multiplied by sigma is replaced by s divided by root n, and it's smaller than x bar plus z alpha over 2 multiplied by s instead of sigma, and then divided by the root n. So that's our confidence interval in this case, and we can establish it very nicely. That's if the variance is unknown, but we deal with a large number of samples. If the variance is known, then as we did in the previous slides, we can go and construct our confidence interval easily, and it follows a standard distribution. So as I mentioned, we'll only focus on, for the case of variance unknown, we'll only focus on the case where a large n and the solution becomes like before. This is our confidence interval that I just mentioned before. The only difference is instead of sigma, which is unknown to us, we just estimate that from the samples using the sample standard deviation. That's it for this part, and I hope that it will be useful for you. It's a very easy part to address, and also we will solve some problems on that on the lecture itself. Hopefully it will be very clear, and solving problems on interval estimations is quite straightforward.